Hi guys, this is Mrs. Allison. You should have your note sheet 10 tube, the parametric equations and arc length. I would love it if you would start with the warm up. So hit pause on the video and try this problem and see what happens. All right, if you had a chance to try the warm up, here is what should happen. So it says find the t-values in which the curve is concave up or concave down in the given interval. We didn't really talk about that yesterday, so let's go over what we know. What do we know about concavity? Well, we know if something is concave up or concave down. In order to find that, we need to be looking at the second derivative. All right, so we're going to start with x equals, and if I'm going to 2t, and if I'm going to take the derivative of that, I'm going to do dx with respect to t, which is going to give me just 2. I'm also going to take the derivative of y with respect to t, which is 2 sine t. Okay, and then the derivative of that is going to be dy dx, which is equivalent to dy dt over dx dt. So I get 2 sine t over 2, which gives me just the sine of t. Now, remember, if I'm going to look for concavity, I need the second derivative. So what I'm going to do now is I'm going to use the formula we said yesterday, which is, I'm just going to write it up here, so is the derivative with respect to t of dy dx all over dx dt. Okay, as long as dx dt isn't equal to 0, but we know that dx dt is equal to 2, so we're good. So I am going to take the derivative with respect to t, derivative with respect to t of sine of t over dx dt, which is 2. Okay, derivative with respect to t of sine of t is the cosine of t over 2, or 1/2 cosine t, depending on how you want to look at it. And I need to check concavity. I am going to have to, I did not leave myself enough room. Okay, I'm going to check concavity. And so to do that, I need to find my critical values. So I need to figure out where, we'll have to just erase this in just a minute, where 1/2 cosine of t is equal to 0. And I know that gives me t values of pi over 2 and 3 pi over 2. And I could keep going, except I'm in the interval of 0 to 2 pi, so we're good there. So looking at a number line, if you are a visual person, if not, no worries. We can't even use a number line on the AP test, and you know that. So looking at this, if I deal with 1/2 cosine of t and I plug in something that's less than pi over 2, I know that my values are positive. Between pi over 2 and 3 pi over 2, the values of 1/2 cosine of t are negative. And then again, 3 pi over 2 to, oh my goodness, 3 pi over 2 to 2 pi, the values are positive once again. So our function is concave up on the interval from 0 to pi over 2 and 3 pi over 2 to 2 pi. And concave down from pi over 2 to 3 pi over 2. Hopefully you did okay on that one. Okay, so I am going to hit pause and erase some of this before we go on to talk about arc length. Okay, so we're going to look at arc length now, and we're going to start with any curve. This would probably have some direction to it. I don't necessarily have any right now, but we want to find arc length. We want to find the length of the curve. So what we're going to do is we are going to start with a very, very infinitesimally small region. I'm going to draw it a little bit bigger than that so you can actually see it. But let's just say that we are finding the curve right here. Okay? And if I want to find that length, and then keep in mind, if that is infinitesimally small, that's essentially a straight line. And so what I'm going to do is I'm going to look at the distance that it goes over. What I know is that that's dx. And then I'm going to look at the distance that it goes up, a tiny change in y dy. Okay, so using the Pythagorean theorem for this, we would get, and arc length is usually s. I'm not sure why, but it is. We would get that ds squared, Pythagorean theorem, we'll call this ds, this change, is equal to dx squared plus dy squared. Okay? Now, if we're dealing with rectangular coordinates, so if we're dealing with what we've been dealing with before, and I want to look at my rectangular, remember that this is just y equals f of x, so everything is going to be terms of x. I would have ds squared over dx squared equals dx squared over dx squared plus dy squared over dx squared. Looks a little silly this way. Let's actually solve it just a little bit. So to solve it, I'm going to take the square root of both sides, and let's simplify it just a little bit. So I would get ds over dx equals the square root of, I'm going to just simplify dx over dx, dx squared over dx squared to 1, plus dy dx squared. Okay, making it look just a little bit different, I may rewrite it as ds equals the square root of 1 plus dy dx, and you'll see why I'm doing this in just a moment, dx. Okay, but if I want to look at the parametric form of this, which is, mind you, what chapter we're in or section we're in, if I want to look at the parametric of this, this is going to be with respect to t. So I'm going to have ds squared over dt squared equals dx squared over dt squared plus dy squared over dt squared. And again, I'm going to go through and take the square root of both sides. Unfortunately, now I don't have any simplifying, or quite as much. So I have ds over dt equals the square root of dx dt squared plus dy dt squared. So simplifying, we get ds equals the square root of dx dt squared plus dy dt squared dt. Okay, so you may be asking, why did we rewrite that? Well, we didn't actually find any arc length. All we did was find this tiny little region. Think back to last year. How do we find the sum of all of those tiny little regions? Well, let's just say that we're going from x equals a to x equals b. I'm going to ignore this example, so pretend this example isn't here right now because I didn't leave myself enough room to write. So we're just going to do this for now. Okay, so if I want to find my rectangular arc length, from x equals a to x equals b, we know that that is just going to be this, the arc length is going to be the sum of all those tiny little arc lengths that we found above added together. And similar for my parametric, it's not going to look much different. Arc length. Oftentimes you see Greek letters for t. So t equals alpha to t equals beta is going to be the sum, the sum of all of the values from alpha to beta of dx dt plus dy dt dt. Okay, so that's how we find the arc length. So now let's look at an example. I'm going to pause this and erase a few things. That's the buildup of how we find the arc length. And then we'll look at an example. Okay, so let's look at an example. Find the arc length of the given curve on the indicated t interval. And we have the function x equals sine cubed of t and y equals cosine cubed of t on the interval from 0 to pi over 2. What you will notice is that this is a parametric function, and so therefore we are going to use the parametric formula for arc length. So in order to do that, I need to know what dx dt is, I need to know what dy dt is, and then I need to square both of those. So let's start with that. Let's start with dx dt. And if I take the derivative of x with respect to t, it's a chain. So I've got 3 sine squared t times cosine of t. And then if I do dy dt, I get also a chain, 3 cosine squared of t negative sine of t. Let's get those derivatives right. And then square each of those. So dx dt squared equals, that would be 9 sine to the 4th t cosine squared t. And similarly, for dy dt squared, I would get 9 cosine to the 4th t. Negative sign will end up being just positive sine squared t. Okay, so now comes the real interesting part. So I'm going to take the integral. Let's make that a little bit smaller. The integral from 0 to pi over 2 of the square root of dx over dt squared. So that is going to give me 9 sine to the 4th t cosine squared t plus dy dt squared. So 9 cosine to the 4th t sine squared t dt. Okay, let's do a little bit of factoring. We've got to make this look a little bit simpler. And I notice that I can take out 0 to pi over 2, the square root of, I can take out a 9 cosine squared, cosine squared t sine squared t, and it leaves me with sine squared t plus cosine squared t. Why would I do that? How does that help me any? Well, we know that this quantity is equivalent to 1. So I'm going to go and rewrite this. It makes my life a little bit easier. That I am really taking the integral from 0 to pi over 2 of 3 sine t cosine t when I simplify that, because that becomes a perfect square. Makes life a lot easier. Okay, and now I am going to use a u substitution, I believe. Let's do that. Yeah. Okay, so I'm going to let u equal sine of t. I'm going to let du equal cosine of t dt. Then u of 0 is 0, and u of pi over 2 is 1. So let's change this integral to be the integral from 0 to 1 of 3u du, which is going to be 3 halves u squared evaluated from 0 to 1, which gives me 3 halves. So the arc length of that curve would be 3 halves. Okay. I would love for you to try this next example and just see how you do. So hit pause and then we'll come back to it. All right, hopefully you had a chance to try this problem. So the first thing that we are going to do is take the derivative of each with respect to t. So dx dt would be 3t to the 1/2. And then if I square that, I'm going to get 9t. And then let's do it for dy dt. dy dt would be, we've got a chain in there, so I'm going to have negative 3/2 8 minus t to the 1/2 power. And squaring dy dt, I'm going to get 9/4 times 8 minus t. Okay, so now I'm going to take the integral from 0, where were my bounds? 0 to 4 of the square root of 9t plus 9/4 times 8 minus t. Actually, I'm going to simplify that a little bit. I don't like that. Dt. Let's see, simplifying that a little bit. If I combine like terms, we're going to get the integral from 0 to 4. That'd be 70. 2 divided by 4 would be 18. 18. And then 9t minus 9/4. So I've got 27/4. It's going to look kind of ugly. Give me a second. 27/4 t plus 18 dt. Let's simplify it one more time. That'll be prettier. And that gives me 3t plus 8 dt. Much better looking. Okay. Let's use a u substitution. Let's actually pull out that 3/2. So let's do 3/2, 0 to 4 of the square root of 3t plus 8 dt. I'm going to let u be 3t plus 8, so du would be 3 dt. So I don't want that 3, so I've got 1/3 du equals dt. And then u of 0 is 8, and u of 4 is 12, and 8 is 20. Okay, so this new integral now is 3/2 from 0 to 20 of the square root of u du. Oops, I lost the 1/3 times 1/3. We'll stick that out front. Okay, and then let's take the antiderivative of that. Let's combine like terms here. So I've got 1/2 times the antiderivative of 820 root u du. Now take the antiderivative. So I'm going to get, let's see, that's u to the 3/2 up a degree times that, 2/3, evaluated from 8 to 20. So I really have 1/3 of u to the 3/2 evaluated from 8 to 20. Well, this won't be super pretty, but 1/3 of 20 to the 3/2 minus 1/3 of 8 to the 3/2. I'm okay with this as an answer. Certainly we could simplify it. Might, depending on the book, depending on the problem, maybe want to put it in decimal form. So decimal form is not pretty. It's 22.272 if we go to 3 decimal places. So how'd you do? All right, we look forward to seeing you next time.